Hi, my name's David Hannaford, and over the next 20 minutes or so I'm going to have a quick chat about the autonomous robots that I've built over the last 50 years or so. I got interested in autonomous robots when I was in college in 1969, and in particular when I came across a book by William Gray Walter called Design for Brain, and that sort of led me into sort of cybernetics and that whole area. William Gray Walter, if you don't know, built some autonomous little mobile robots in 1948 that he called tortoises, and they moved around and they could, in a very limited way, explore the environment that they were in. Anyway, that's what got me interested in little autonomous robots and led me to 50 years of playing around with them, building with them, entering competitions and all sorts of other things. What I'll do is I'll show you on the screen images or videos of 10 of what I think are my most interesting ones, and alongside I'll chat about them and tell you what they were, when they were built, what they did, and some of the interesting features. Okay, so over to the first one. This one's looking pretty battered now, but it was the first one I built. As you can see, it's from Meccano. It's all analog, no digital, and basically it used a number of relays which we'd salvaged from the college's juice computer to do the steering. Basically, when it hit things at the front, it backed off, turned around, and then trundled off in different directions. Nothing very spectacular, but it was interesting, and it got me started on building the first of my autonomous robots. My next robot took a little while coming. I suppose I got on with life. I was involved with computers and, amongst other things, running a small team of people building artificial intelligence expert systems in the mid-90s. So it was about 2000 before I started looking at building robots again, and the techno games came up as an option. I watched the first techno games in 2002, and when I heard that they were going to be repeating it in 2003, I thought, here's a good chance to build something interesting. So I went for this four-legged walking dog to compete in the sprint race. It was programmed in assembler for a PIC 16F877 microprocessor, and it used 8 servos for actually making the leg movements. We also had one servo in the middle of the body that allowed it to bend right or left, and we could use this for steering it to make sure that it stayed straight as it went down the track. I spent about 6 months looking at how small animals walk, especially little dogs, all the bone structures and everything, and then tried to mirror that with little pieces of bent aluminium and servos. Eventually we got it running, and we took it to the competition, which was filmed in December 2002 and actually shown in March 2003. We were competing in our heat against a robotic cow and a robotic penguin, and unfortunately we were a little on the slow side, and the cow beat us to the end of the course. Here is a short clip of it in action.
Daisy the cow is back. Animatronic athletes.
Fairly slow race.
When it looked like Techno Games wasn't going to run again, I had to look around for another competition, and I spotted the Melexis Safety Trophy competition, which was being run in Belgium. On this competition was to first of all find a yellow tennis ball and capture it, and then carry it by whatever means down to a flashing beacon that was about 20 meters away down a course, which was littered with concrete blocks and also cans sitting on top of egg cups. Some of the cans were hot, and some of them were cold. You got points for knocking over the cold ones, but you didn't have to knock over any of the hot ones. quite a complicated little challenge. The top of the robot had two CDs with a ring of phototransistors inside, which it used for detecting in which direction the flashing beacon was going to be. The robot was quite large, so it needed a bit of power for the motors, and we used two electric screwdrivers to power the two main wheels. The motors were controlled by relays to go forward and backwards, fast and slow. To detect the objects, we had a rotating rod on which were mounted four laser pointers. These were all at different heights, corresponding to the heights of the different objects that we had to detect. And lenses in front of 35mm film cans amplified the returning reflection from the objects back to a phototransistor associated with each laser. The lasers were modulated at about 1 kHz, and there were tuned amplifiers for each of the four lasers to pick up the returning signal to make sure that it was just getting the reflection back from the laser and not anything else. There were also sensors on the bumper in case it did actually run into anything, and downward looking floor sensors to make sure that we didn't go over the edge of the track, which was delimited by a silver line. There were two PIC microprocessors, both programmed in assembler. One of them handled all of the stuff coming back from the phototransistors to determine where the objects were and which direction we needed to be heading. And then the other one was basically controlling which way we ought to be going and controlling the motors to make sure that we actually went where we wanted to go. At the bottom of the robot was a curved arm which could be moved out. This was driven by a mechanism from a salvaged CD player. Then when it found the tennis ball, it would move out the arm, spin the robot round to collect the tennis ball inside the arm, bring the arm back again, and it's captured it, ready to take it down to the rest of the course. Here's a short clip from the Belgian news report that was on the local television that evening.
Simpel. Blauwe kegels moet je omstoten en de rode net niet. Het wordt iets moeilijker als er geen afstandsbediening is om de robot te besturen.
Ik weet niet wat het wel is, maar ja, het is een oog.
When the next Melexis safety trophy competition in 2005 was cancelled, I looked around for something else to do, and I came across Micromouse. The Micromouse competition has been running in the UK since 1980, and basically the idea is to get your autonomous mouse to go from the start in the corner of the maze to the goal centre in the centre of the maze as fast as possible. There are a couple of different variations of it for different levels of expertise. The simplest is contact wall following, where you run along basically the left-hand wall and it takes you to the centre. Slightly more complex is non-contact wall following, so you're basically still following the left-hand wall, but you're doing it without touching it. And then the most complex, which is non-contact maze solving, where you basically determine the optimal route from the start to the centre, then go back to the start and you run that as fast as you can. So this is the first Micromouse that I built. It's a simple contact wall follower, which I built after I'd been to the 2004 UK national competition in Birmingham. Basically it's just two servo motors with the end stops removed so that you can continuously rotate them, a microchip PIC microprocessor, and 3 micro switches, 2 of them basically allowing you to keep a distance against the left-hand wall, and the one at the front just to detect the wall in front to know when you need to turn right. Over the next 5 years, I built another 6 mice, trying out various combinations of motors, sensors, layouts, and all that sort of stuff. What I particularly learnt was that ultrasonics and vision-based systems were typically far too slow. Controlling a Micromouse at speed, you need to be measuring all of your distances around you about 1,000 times a second or more. It helps to have good motors with encoders so that you can measure how far you've gone and how fast you're travelling. It also helps if you have some nice sticky wheels so that you don't slip when you're accelerating or decelerating. Most current mice sense the distances from the walls using a pulse of light from an LED and then measure the amount of light that comes back. The majority of mice tend to use infrared light as it's less affected by natural light around in the arena. But this mouse, Erratic, uses visible light, and in fact it uses a combination of LEDs which produce a fairly large spot, and also some small laser pointers which produce a smaller spot on the wall, which helps you to detect the ends of walls more accurately. It has a gyro to measure the angle of turn, and you can see the display on the top, which allowed me to see what was happening basically on all the sensors and the wheel counts from the quadrature encoders. This has been one of my best Micromice so far, and it got a 2nd place in the non-contact wall following competition in 2009. In 2012, I started running an after-school robotics club at KES School in Stratford-upon-Avon. In 2013, we decided to enter the Toyota PIC Challenge. A kit was available from Rapid, which had a circuit board and all the components that needed to be soldered in, plus a couple of motors. The robot then had to be built, and you programmed it in PIC Basic. The challenge was to navigate your robot across a relatively simple maze in the shortest time. There were entries from, I believe, over 200 schools, but only the best described ones got a chance to actually run in the regional heats and then attempt to have a go in the final. A team from Kettering College in Essex won the £1,000 prize, and they were very happy. As well as running the robot club at Stratford, I was also helping to run an Imagineering club at a local primary school. One of the Imagineering club projects that I designed was to put together a roving robot. We used a laser-cut acrylic chassis that I'd been involved with at Birmingham City University, and matched this up with a small PIC processor and an L293D dual H bridge for controlling the motors. In week 1, the students would assemble the motors and the chassis and get the basic running items working. Then in week 2, we used a prototyping board, and we would put together all of the electronics that were required to control the robot. The PIC processor was pre-programmed to accept a sequence of movements, forward, backwards, spin left, spin right, those sort of things, from a couple of tactile switches which are mounted on the prototyping board. So then in week 3, the students could program their robots, and we used to play Robo Skittles, where you basically use the robot to knock down as many lemonade bottles arranged like a Skittles game basically across the other side of the room. This chassis was particularly versatile, and we ended up using it both at KES and at the primary school for line followers, using BBC microbits, Crumble processors, Arduinos, and all sorts of other processors. If you want to look at the DXF files for the chassis, these are available online at www.davidhannaford.com/KES/. One of the most successful Micromouse in the UK around about this time was a mouse called Decimus, produced by Peter Harrison. Peter let me have a copy of the circuit board that he'd produced for his mouse, and I used it to produce my mouse called Quadratic. I used different motors, batteries and sensors to Peter's, but the layout was pretty much the same. The idea of using a four-wheel drive mouse was to improve traction upon the baseboard that we're running upon, and to allow us to accelerate and decelerate and go around the corners faster. A Faulhaber motor on each side of the robot drove the two wheels on that side through a gearing of about 3:1. That gives a potential speed of up to about 3 meters per second. The main processor was an ST Micro, and it was my first chance to actually produce a mouse that was coded in C. The ST Micro has got lots of processing power, and I was also able to handle the Quadratra encoders from the two motors, which gave us accuracy of within a millimeter or so on position of the robot. 3 sets of visible light sensors were installed, one looking forwards and the other 2 looking sideways at an angle. The sensors used a pulse of about 100 microseconds, and every millisecond all of the 3 sets of sensors plus the encoders and the gyro were read, and the position calculated at that point in time. On its first outing in 2014, it managed a very respectable second place in the non-contact wall followers competition. In 2017 and 18 at KES School, we built robots for Pi Wars and also for line following in the IET and Micromouse competitions. But the next one that I want to show you is our entry for the 2019 Pi Wars Challenge competition, a robot called KESBOT 2. As required by the competition, the main processor was a Raspberry Pi, the 3B model, and we had a mass of sensors to enable us to complete as many of the challenges as we could. So on the front we had some ultrasonic sensors which could measure the distance to the wall in front. On each side we had infrared light wall sensors which basically would pick up the light coming back bounced off the walls at the side. That would enable us to run along a wall at a fixed distance from it. We also had a couple of line following sensors looking downwards underneath the robot for the line following challenge, and we also had a camera mounted on the top which could help us with the color challenge. For the remote control challenges we used the Pi Hut gamepad wireless controller. which fortunately came with a series of routines that we were able to modify to enable us to control the robot fairly easily. For the Space Invaders challenge, we had to knock down a number of Space Invader looking like targets. An attachment on the top of the robot had a cartridge that would hold 5 Nerf bullets, and at the bottom of the cartridge was a little gap through which a pusher rod could push one of the Nerf bullets forwards into 2 spinning discs. The discs were 3D printed and were contoured to the shape of the sides of the Nerf bullets, and as the Nerf bullet touched the 2 spinning discs, it would be shot forwards. Once the Nerf bullet had been shot out, the pusher rod will be pulled back. This was controlled by a servo, and that servo was being controlled by a little Arduino. It was a very effective way of shooting out the Nerf bullets at the target. By managing to complete nearly all of the challenges, we managed to come 5th out of, I think, about 37 schools who were competing in the competition. Around about 2019, a group of us at the UK Micromouse and Robotics Society decided that we wanted to design an open source entry-level robot for line following and maze challenges at the Micromouse competitions. In early 2019 we had produced the first circuit boards and built the first prototype versions based upon the designs that we had. We documented the parts and in detail the build process and made these available online. In September 2019 we decided we would try these out at KES School in the Robotics Club. 10 students each built one main circuit board and also a line follower sensor attachment. The plan was to run these at the IET and Micromouse national competitions during that academic year, but COVID-19 got in the way. However, we did manage to run some at a virtual UKMARS competition in 2020. The robot uses the commonly available N20 micro-geared motors with the option of putting encoders on the rear shafts. It uses the SparkFun TB6612 FNG motor driver board and an Arduino Nano processor to control everything. At the front you can plug in different sensor boards either for line following or for wall following or potentially maze solving. If you're interested in UKMARSbot, there'll be a separate presentation on that, and also there's lots of information available at ukmars.org/project/UKMARSbot. I hope you found that interesting. If you want to know more, you can have a look on my website at www.davidhannaford.com/robots. Okay.